thermodynamics, or the study of heat, heat dynamics, moving heat, and so really we're looking at heat transfer. But let's just dive right in. So first off, there's a difference between temperature and heat. Temperature, which we abbreviate with a capital T, is really a measure of the average kinetic energy of the particles in a system. Those of you that have taken chemistry, you've heard this before. But temperature, you can have some particles moving fast and some particles moving not so fast, and overall, in the end, that averages out to some average kinetic energy. And so really, when we measure temperature, we're measuring how much are the atoms in there vibrating or moving, and it's an average motion energy. It's measured in degrees Celsius or in Kelvin. Kelvin is an absolute scale, so that there's no negative numbers. And it turns out there's an absolute zero, an absolute coldest temperature that we could possibly reach. It's negative 273.15 degrees Celsius. On the Fahrenheit scale, it's around negative 465 degrees. And so we just said, let's call the absolute coldest temperature 0 and count up from there. And so that's what the Kelvin scale is, and the conversion to convert between Celsius and Kelvin is there. And that, of course, can go on your formula page. One thing I want to point out at this point is that Kelvin is not technically degrees Kelvin, and there is an English equivalent. It's called the Rankine scale. Also, they do not call it degrees Rankine, but just Rankine. Heat, instead, is a measure of the total thermal energy of the system. So heat is more of how much energy is there in the whole system. Heat's also known as enthalpy, and unfortunately, we can't actually measure the total heat content of a system. Usually, the reason for that, although this is a little bit oversimplified, is just because we can't get rid of all the heat in a system, and it's only through getting rid of all the heat that we could measure how much heat energy it had, and then it's kind of useless because it no longer has it. Moving on. Heat is abbreviated with the letter Q. I have no clue why they chose that one, and so there you go. The analogy I always like to give is that if I have a bowl of soup and I have a big heavy metal spoon in there, and I pull out a spoonful of the soup, as long as I waited initially when I put the spoon in and let everything reach an equilibrium temperature where everything was the same temperature, when I pull that spoon out, the instant I pull it out, the spoon and the soup in the spoon all have the same temperature and have the same temperature as the bowl. Now, of course, they're going to start to cool, but we're going to ignore that initial cooling. The instant I pull it out, they all have the same temperature. But the bowl of soup has more heat energy than the spoon does because there's more stuff there. And so heat energy is not just related to how much the particles are vibrating, but also to some extent how many particles are there. Also, if we look at just a spoonful of soup and the spoon itself, and if we say that they had roughly the same mass, probably not in the real world, but if we found the exact right spoon so that the mass of soup inside of it was the same as the mass of the spoon, we're talking either tiny spoon or a tiny spoon or massive amount of soup in this spoon. But either way, if they have the same mass, it turns out that the soup still has more heat energy, because even though there's the same amount of stuff between the two, the soup has a higher specific heat capacity. It has a higher ability to hold heat, meaning it takes longer for it to heat up. It also takes longer for it to cool down. Metals warm up and cool down very quickly, and because of that, they don't actually have a lot of heat energy inside of them. Anyway, we can use all those facts together to calculate the change in heat of a system, and that is equal to mass times specific heat capacity times change in temperature, or delta Q equals mCp delta T. And it's measured in joules or in calories, where joules is an energy unit and calories is kind of a special heat energy unit. And there is a relationship between joules and calories. As a side note, technically speaking, delta T's changes in temperatures are Celsius degrees instead of degrees Celsius. It's just a way of noting it, and so that if we talk about a system undergoing a so many Celsius degree change, then the degree kind of after the unit implies that it's a change instead. And I'm gesturing these backwards to the screen, so we're going to try to flip that. Just as a side note, changes in temperature are measured in Celsius degrees rather than degrees Celsius. And it's just a matter of where we put that degree sign, but temperatures are in degrees Celsius or degrees Fahrenheit, and changes in temperature are in Celsius or in Fahrenheit degrees. It's just a minor notation thing. It's not something I'm going to be picky about, but it is technically the way that they should be reported. Anyway, specific heat capacity, abbreviated as C subscript P, is the amount of heat energy it takes to raise the temperature of 1 gram of a substance by 1 degree Celsius. And because the steps on Celsius and Kelvin are the same, we could also say it's by 1 degree Kelvin instead. For water, the specific heat capacity is 1 calorie per gram degree Celsius, or 14.18 joules per gram degree Celsius. And of course, we put Kelvin instead of degrees Celsius in the denominator there. And a calorie is actually defined as the amount of heat energy it takes to raise the temperature of 1 gram of water by 1 degree Celsius, because many of the metric units were originally based off of water. Also, as a side note, you've heard calories before, but you've heard of big C calories, which are food calories, which are equal to 1 kilocalorie or 1,000 heat calories. And we've mentioned it before, but conductors are materials that easily conduct heat energy, and insulators are ones that resist changes in heat energy. Because of that, it's really a clue to their specific heat capacity. Conductors have low heat capacities, and insulators have high heat capacities. Water is decently high, which means most heat capacities we work with are actually decimal numbers smaller than 1. But that's just the way we define the units in the metric system. What that means is that it's very easy to heat up a metal, but it doesn't have a lot of heat energy in the end because it doesn't take a lot of input of heat energy to get its temperature to go up, and it gives off that heat very readily. It's where the old phrase, if you've ever heard it, a watch pot never boils, comes from, and I'll explain that phrase in class instead of elaborating here. Latent heat is a special type of heat. It's the amount of heat that must be applied or removed from a substance to change its state of matter. And what ends up happening is that when a substance is going through a change in state, the temperature actually plateaus. So if we have water ice and we start heating it up and heating it up and heating it up, it'll go from negative numbers up to 0 degrees Celsius, and then at that point we could keep putting in heat energy and keep putting in heat energy, but the temperature stops going up. And instead what happens is all that heat energy goes towards breaking the bonds between the molecules. Not the bonds inside the molecule between the hydrogens and oxygens, but the bonds between one water molecule and another water molecule, until all the ice has melted. And then once all the ice has melted, then the temperature will start to go up again, and we'll be heating a liquid. And then at that point again, the temperature will plateau as we get to the boiling point, and all the heat energy is again going to breaking bonds between the molecules. But latent heat is the amount of heat necessary to change state of matter. And I have the specific values here for water: the latent heat of vaporization, which is the boiling one, and the latent heat of fusion, which is the freezing melting one, units there. And those constants can also go on your formula page. This brings us to a heating curve. Again, for those of you that are taking chemistry, you've seen this before. You could probably skip this whole slide, but you may want to jot it down again if you don't remember it. So here is a heating curve, and I do recommend actually sketching this heating curve. I have it labeled A through E on the diagram here. Rather than labeling it like that, though, I would actually label it with the labels I have over here on the side, with where A is heating a solid. So here we have a solid, we're heating it up, and then we get to the melting point, and then we have both solid and liquid. And then we get to the heating a liquid, and then again we get to the boiling point where we have both liquid and gas, and then we get to where we're just heating a gas. If we did the reverse process, then this would be condensing here at D, and B would be freezing. But that is a heating curve, and this specific diagram with the numbers on it is for water. Though the slopes are different and the widths of the flat segments are different for other substances, the shape is the same. Also, as a side note, as I said already, heating can be cooling. For the slope parts, we'd use the formula that you've already seen, Q equals MCP delta T. And for the flat parts, the straight line parts for phase changes, we'd be using the Q equals M times the latent heat formula. And as stuff heats up or cools down, we could talk about the ways in which they heat up and cool down, the ways in which the energy is transferred between them. And there are three different types of heat transfer. One is conduction, and conduction, it requires direct contact, two things touching one another. Conduction is very common with solids, but it does happen with solids in other states. Anywhere where two things are touching, they transfer heat by conduction. Fluid heat transfer is convection, and this is the process of heat rising, cold sinking, heat rising, cold sinking, heat rising, cold sinking. It's where the old adage that hot air rises comes from, though that turns out that's not totally true. Hot air rises because cold air is more dense and sinks down and pushes it up, and if you have nothing but hot air, the hot air is not just going to rise and leave. You do have to have a temperature gradient or a difference in temperatures for that to happen. Anyway, fluids, as a reminder, are liquids and gases, and pretty much any state of matter that's not a solid is a fluid. And so convection happens usually in fluids. And lastly, radiation requires no contact, and this is a type of light that's being given off instead, infrared light, and that light then transfers its energy. Radiation can go through a vacuum, that is, it doesn't have to have matter to go through, it can go through empty space. This is how we get our heat energy from our sun. I like to think of putting a pot on the stove for these three different types of heat transfer. So you put a pot on the stove, and where the pot is touching the stove, and right where the liquid inside your pot is touching the pot, that's all conduction. Inside the pot, though, if you watch, especially if you put something in there like tiny noodles or rice or something like that, you can actually watch them rise and fall. You might see some bubbles even get caught on a circulation, but if you put something in the pot, you can see it rise and fall, and that rise and falling, heat rising, cold sinking, is convection. If you're standing above it, you're probably getting conduction from steam and some convection currents heating your hand, but if you're standing beside it, heat tends to rise, but you'll still feel warmth. That warmth that you feel off to the side is radiant heat energy. It's infrared heat energy. And that's where we're going to pause this presentation, and if you have any questions, be sure to bring them to class.